In video two of this second dose of motion problems, we're going to take a look at a very subtle difference when we are using integrals to find um, motion motion measurements. But so let's read the problem so that we can kind of get the idea of what we're looking at, what we're given, and then what they're asking for, so that we can make sure that we're on the right track. Mr. Brust is driving across town to Mr. Sullivan's house to play with a new set of Star Wars figures. Wow, it sounds like someone's having a good weekend. That sounds mighty fun. Mr. Brust's speed would obviously vary throughout the drive, but because he is so cool, he came up with a function that represents his velocity in miles per minute at any time t minutes since he left his house during the 30-minute drive. So, two things. We're given the velocity function in equation form, and we're seeing the velocity function graph in a window that goes from 0 to 30, so that's the complete drive, and then -3 to +3. So notice, the velocity is the velocity graph is telling us that at some point actually at the beginning, the velocities are negative, velocities are positive, velocities are negative, velocities are positive. So what does that mean in terms of the situation? Think about what we said about velocities and the sign, as in SIGN, positive or negative, of the velocity. Remember that if a velocity is negative, that means it's moving to the left or away or in one direction. But if the velocity is positive, it's moving to the right or towards or in the other direction. So that means Mr. Brust, who's driving to Mr. Sullivan's house, was going in one direction at the beginning, but then right around here, he changed directions because now my velocity is positive and he's moving in another direction. But then it changed again, and then it changed again. So he's not going straight from his house to Mr. Sullivan's house. But let's see what we know, or let's see what they're asking us for. Set up expressions for the following scenarios and then use a calculator to solve. Perfect. How far is Mr. Brust from his house after 10 minutes? Okay, so to figure that out, we're going to take the velocity function and we're going to take the integral from 0 to 10 of sine of 0.3t plus the natural log of t plus 1 minus 2 dt. Why are we doing this? Because this is the velocity. And if we go backwards, we're going to get position, but we're actually going to get the change in position, which is going to give us the displacement that we're looking for. Also, just another note, whenever the function is named, it's given and it's named, you could save some time for writing all of this and just say the integral from 0 to 10 of v of t, because we have the name of the function already given to us. Or you could write it, you could give it a name and then refer to that name. But it has to be labeled, and it has to be clear what you're talking about, right? So here, this is what we're going to put into our calculator. So I went to my calculator, and I went ahead and pre-typed in the whole equation. I'm sorry, I moved this. I went ahead and pre-typed the whole equation in y1. Why did I do that? So that when I go to the home screen, I don't have to type it all over again. I can just say math 9 from 0 to 10, and then I can just say, hey, calculator, remember the function I asked you to say for me in y1, and then just call it y1. So very much like here on the paper, instead of writing all of this, I'm just referring it to by its name, v of t. With a calculator, I called it y1, so I'm going to ask it to remember y1. The way you do that, the way you pull up the names, a quick way to do that is to do alpha trace, and it gives you all of the lists, all of the names of all the equations, but we put it in y1, so I'm going to select y1. So I'm telling the calculator, take the integral of the equation y1 from 0 to 10. I'm going to press enter, and I get 3.0101. So let's round it to 3 decimal places, but I'm going to put all 3 decimal places, 3.010. 3.010. Now, what is the unit of this? Well, we were taking velocity, the integral velocity, and velocity was measured in miles per minute, but the integral is going to multiply miles per minute, which is what this is, times dt, which is in minutes, and so I'm left with miles. So this is how far Mr. Brust is from his house after 10 minutes. He's that many miles away from his house. Alrighty. How far is Mr. Brust away from his house after 15 minutes? Well, let's see. We're going to set up the integral from 0 to 15 of my function v of t dt. It has a name, so I'm just going to use it. Similarly, on my calculator, I have saved it, so I'm going to use it. I could also just do a copy paste. If I move up and highlight that entry, I can just press enter, and then I can go back and change that 10 to 15. Press enter. I don't even need to get out of the integral. You can just press enter now, and you're going to get 3.397. So this is 3.397 miles. So did he go, is he farther away from his house after 15 minutes? Yes, he is. Great. If Mr. Brust arrives at Mr. Sullivan's house after 30 minutes, how far away does he live? Okay, so how far is he from his starting point? And his starting point was his house, right? So here we go. We're going to take the integral from 0 to 30 of v of t dt. And we should get a number that's a little bit bigger. Again, I'm going to copy paste and just change that to 30. And here's my answer, 22.824. 22.824, and these are miles. Now, let's talk about what we're really finding. Remember, the first part of the fundamental theorem of calculus says, if you can find an antiderivative of velocity, then I can substitute the top and substitute the bottom. So in reality, what we're finding is the antiderivative of velocity is position. I call it s of t. So I'm going to say s of 30 minus s of 10. S of 30 minus s of 10. So the position of where, I'm sorry, 0, not 10. So the position where he ended minus the position where he started, that tells us how far apart, how far away he lives, right? But the reality is that's not how much he drove. Because remember, he was driving in one direction and then he went in the other direction and then he was driving in the first direction and then he went back to, so I think he got lost along the way. And if you think about what the integral is finding, it's finding this space here. So all of this red area that I'm shading in the first whatever minutes this is, he's going in one direction. But then he's going in the opposite direction, all of this. So somewhere here, I don't know, maybe there, like this and this cancel each other out. So then he's truly only going in towards Mr. Sullivan's house. Oh, but then he got lost again, and now he's going in the wrong direction. Not wrong direction, but I should say the another direction. And then he goes back to the full thing. So what we just found is takes into account the fact that he went one way, then he went the other, then he went one way, then went the other. So this is just like, hey, where he started, where he ended minus where he started, boom, that's what it is. But that's different than the last question. The last question is, how many miles did he actually drive? Right? So this is his displacement. What we're looking for is his distance, which means I need to find out what is this area, because that's how much he moved in one direction. But instead of it being negative, I need to make it positive so that I can add it to this area. So I can add it to this area. If I can make it positive, add it to this area. Well, how do we make things quote unquote positive? How would I make this actually be like up here? And how would I make this to be up here? And therefore I would have this area positive and this area positive, and all of these green areas would be the accumulation that would be the total distance he actually traveled, not just his displacement. Well, the way I do that is with an absolute value. So I need you to write down, when we take an integral of velocity, we only get displacement, right? The change in position. But like we saw, he might have gone in one way and then another way and then back and he got lost. So the total distance is found by taking the absolute value of velocity. Notice the absolute value has to be around velocity, not around the whole thing. we're taking the integral of the absolute value of velocity. Also, don't forget, the absolute value of velocity actually gives us speed. So without the integral, absolute value of velocity is speed. With the integral, the integral of the absolute value of velocity is distance. So going back to letter D, how many miles did he actually travel? Well, he went in the first 30 minutes, because that's how long it took him to drive there, the absolute value of this dt. That's what we need to figure out. And so in theory, if we think about it, the total distance should be more than the displacement, right? This one just factors in where he started, where he ended, and the distance between them. But this, since he went off course when he got lost, or he went one direction, I don't know why, then we need to see a number that's bigger than that. So I'm going to come over here, and I'm going to say we're going to take the math 9, we're going to take the integral from 0 to 30 of the absolute value of my equation in y1. So absolute value lives in math, and if you go over to the number menu, abs is the absolute value. And then I want to say, calculator, remember the equation I saved in y1, so I alpha traced it in there, and then that's going to give me, oops, I didn't move over, that's going to give me the total distance he actually drove. 28.497. 28.497 miles. So he actually drove that many miles, even though his house is only 22.824 miles from Mr. Sullivan's. And the reason is he wandered off, got lost, maybe he had some other errands to do, I don't know, but it wasn't like a straight shot from there to there, right? So this tells me the total distance that he actually traveled. So big idea on the bottom of this paper, the difference between displacement, which is just the integral of velocity, versus total distance, which is the integral of the absolute value of velocity.